Buenos días.
Good morning,
Buenos
Sonia.
días.
Yo no venía.
Good morning, Maria Inés.
Morning, how are you?
Hello.
Not too bad. Okay, we are on time. Good morning, everyone. Good afternoon to all of you. Today's presentation is regarding the use of Plecs software for solar energy application. I would like to give a warm welcome to all of you to this new session of the Worldwide Energy Network. In this opportunity, the speaker will be Brian Lieblich from Plexim. He joined Plexim in 2018 as a real-time simulation engineer. His main responsibility are developing simulation models and controls for power electronics applications, creating control software and hardware for HIE platforms, and helping Plexim customers be successful through custom engineering service and technical support. In addition, we have invited as the panelists to Professor Félix Rojas from Universidad de Santiago, Chile, and Professor Carlos Baier from University of Talca. Both of them have experience in the use of this software, so they support this presentation, and they will provide also their opinions regarding the use of this software. I will give the chance now to for you to write some questions during the presentation in the chat or in the chat also of our YouTube live. After the presentation of Brian and the comments given by Felix and Carlos, we will replay all of them. Brian, thank you very much for being supporting our activity, and now the screen and the microphones is yours.
Great. Thank you, Marco, and other members of the Worldwide Energy Network for organizing and participating in this event. I'm excited to talk to you about Plecs and kind of how it fits into the use of simulating solar systems. So let me share my screen here, and so you should all be able to see my monitor.
Yes.
And I just want to give a quick outline of today's talk. So first of all, I want to give a quick introduction to Plecs for those of you who are unfamiliar, and a bit about our philosophy towards modeling power electronic systems. Then we'll discuss kind of at a very high level the components of a conventional standalone PV system, just so that we kind of have a common understanding of some of the models that we'll discuss later. And then we'll dive into modeling the PV array itself. And so we'll build up a model together in Plecs just using basic components, kind of a primitive model. And then we'll take that basic model and we'll use it in two kind of more practical systems. So one would be a single phase inverter that will model a partial shading condition. And we'll spend quite a bit of time talking about the controls that are implemented. And then we'll close out with a live demo of a hardware in the loop of a 3-level NPC inverter, neutral point clamped. And so in that case, we'll perform a desktop simulation on the real-time simulator I have, and we'll actually also generate embedded control code for a TI microprocessor. So with that, if you're unfamiliar with Plecs, Plecs is the tool for fast simulation of power electronic systems. And by system, I mean the power converter with the switching elements, the electrical circuit, as well as everything that the converter is connected to. And for simulation speed, Plecs is based around the idea of an ideal switch or instantaneous switching. And it simplifies the non-ideal effects associated with switching dynamics. And this because kind of when you're looking at things from the system level, say in a PV system running simulations over longer time, looking at the controls, how they interact with the grid. The switching transient details tend to slow down the simulation and kind of don't add much to the behavior that you're really interested in studying, which is again kind of these large signal behavior, these longer term dynamics. So the net result is that it's kind of a fast simulator intended for offline simulation, but also this ideal switch approach is well suited towards real time. And we also have multiple physical domains and controls domain as well. So controls in the analog or digital world, analog digital implementations. We also have the ability to include, say, C scripts. So you can prototype controls that you would eventually deploy to a microprocessor. And then we also have a one-dimensional magnetics domain. So you can create magnetic structures using turns numbers, cross-sectional area, material properties. There's magnetics domain, so or the mechanical domain. So not particularly relevant in solar applications, but if you're looking at wind turbines or drivetrains, electric vehicles, and so on, it's helpful to model one-dimensional rotational and translational systems. And then lastly, there's the thermal domain, where on top of this concept of an ideal switching transition, there's a lookup table-based approach where we can extract the losses from thermal devices, from switching devices, and look at temperatures within the system, losses, and maybe design cooling systems on top of that, determine if our devices are appropriately sized, and so on. So this example here is just a wind turbine model. So you can see you have the two power converters, rotor side and grid side converter here, some filtering, and some of the components would be, the blades would be implemented in the mechanical domain. And you could have, say, this transformer designed here using magnetic components. So one common application space for Plecs is in the design and analysis of power converters associated with PV systems. And so this slide shows kind of an example of a standalone PV system showing the major components one often finds. And again, it aligns with the examples that I'll talk through today. So going from left to right, you have the PV panels. And then maybe some filtering associated with that. Then you would have a DC-DC converter that would regulate the PV panel voltage, and it would connect to typically a higher level voltage for the kind of DC-AC to connect to the grid, and there'd be filtering components, step-up components associated to connect to the grid voltage. And then on top of that, there's lots of controls. So regulating the DC-DC converter, trying to extract the maximum amount of power from the PV panels, ensuring that any regulation function on the AC grid side is happening correctly. And again, it's important to note that this is just an example. There are many, many different topologies, for each one of these subsystems for the DC-DC converter, DC-AC, filtering. Power electronics engineers are always trying to minimize the size of bulk capacitors, of any filtering components, any transformers. So there was a previous presentation from Professor Samir Kuro, and he highlighted industry trends in a previous webinar in the series. So for kind of diving more into the different variations of this topic, I think we're not going to go into that too much today, but just to have a basic system so that we can understand and discuss. So first, we're going to focus on just modeling this PV panel, and then we'll look at what this looks like in an overall system. So when designing the PV systems, it's important to have a useful model of the PV panel array. And so the production of the PV panel, I'm sure as many of you know, is a function of many things, but it is also a function of the intensity of the sunlight hitting it or insolation, the voltage at the terminals of the PV panel or PV array. And I'll try and use the term PV array, which is kind of any number of PV cells or PV panels that are connected in a series parallel combination. So I said it kind of connects to the input port of the DC-DC converter. And then the production of the PV panel is also a strong function of temperature as well. So you kind of end up with a set of nonlinear curves that would have the characteristic kind of shown here on the right-hand side. So you'd have a short circuit current over here. We'd have kind of 0 voltage and maximum output current. You would have the open circuit voltage. You would have kind of maximum voltage with 0 current flowing through it. And then these curves, if you kind of imagine a projection onto the Z-plane, you would have that also be a function of sunlight intensity, as well as another set of curves with that as a function of temperature. So in modeling a PV system in Plex, there's kind of 2 common approaches. One is kind of taking the fundamental equations of the system and implementing that using basic components in Plex. And then the other approach is using a lookup table based approach. So you would basically generate the lookup table beforehand, either from measurements of a system through kind of iterating through these formulas and kind of covering the range of operating conditions you'd consider. And so those are kind of the two common ways. So on the left-hand side is this reference. One of the common ones cited in literature is from Professor Villalba. And we'll go through implementing this in a basic model. And then we also have, if you're interested in looking at the lookup table-based approach, there's an application note on the Plex website that discusses that in more detail. So in the Villalba paper, they break apart PV generation into IPV, which is the current generated from the incident light, and it's directly proportional to the irradiation. It also is a strong function of temperature. And then it uses a single diode here, this ID, and that models the PN junction of the panel. And that's with the kind of the Shockley equation, where IO is the reverse saturation or the leakage current of the diode. And then there'd be shunt and series loss elements. So this RS and RP. And so this last term here is again associated with this current through this parallel resistance. So with that, I actually have let me see if I can just go back and pull up Plex here, and I'll try and hide this a little bit. So make it so we can see this slide and Plex at the same time. And let me just open Plex up. And so if you are unfamiliar, Plex is based off of kind of a drag and drop approach for adding components to a schematic. So we have a library on the left-hand side, and it has components again for the electrical domain, thermal, mechanical. And so if we want to search for something, trying to build up this subsystem here, this PV array, we would say search for a resistor here, and we can drag and drop it into the schematic. And so we can add this RS and see if I can make this a little bit bigger for you guys. You can zoom in. And if I'm going too fast, please slow me down or let me know. And I can talk through things in a little bit more detail. And you can just copy and paste components. So just copy and paste. And we can add this RP. And then you can also just start typing things directly into the editor and search for them. So for example, if we want to have this current source, IPV, you can just start to type on the schematic for current source that's controlled. And so we'd have one modeling the PV generation, and then we'll have another one modeling the diode current. And it'll just be oriented in the other way to make entering the convention a little bit easier. And so we can start to connect these components up to create a schematic. And then what we'd want to do is we're going to have a voltage measurement here, right? So the voltage kind of the current from this diode equation is a function of this voltage terminal. So just to describe this equation a little bit more, this V here is the voltage across the DC connection of the panel. The I is the current injected at this terminal as well. And then VT is the thermal voltage. So it's a function of several physical constants and the temperature, as well as the number of panels or cells that are connected in series. And then this alpha component is an ideality factor that kind of just changes the shape of the VI curve, how it connects the open circuit and short circuit conditions. So we have the voltmeter there, and we also want to have a current measurement. So we can have an ammeter. And in order to test that we're generating this VI curve correctly, we can also add a controlled voltage source here. And so we can basically sweep the conditions at the terminal and see how the voltage and current respond in turn. And I can also just flip this component here just to make it a little bit clearer for when we finally generate it. And so for sweeping the voltage, we can also just use a quick ramp component here. And so we'll sweep this voltage at the terminal from the 0 voltage, right? So the initial output will be 0, and then the open circuit voltage for this panel, I think, is 32.9. So we'll sweep it up to the open circuit voltage. And then what we can do is basically just start to use these constants in this formula to quickly create, a functional model for a PV array. So the first component would be the photovoltaic current, which comes from the light. So that would be a function of a constant, which will of the light intensity, which we'll use just a constant to describe. So we can call this GN, which would be the normalized light intensity for the panel. And then this IPV constant, we just model using a multiplication or a gain, and drag and drop it. And we can call this IPV prime. And we can have this be 8.214 amps relative to the normalized intensity. And so here, again, as this, the insulation will go up and down, then you'd have different levels of generation from this current source. For the diode current, it's a function of this terminal current as well as the voltage at the connection. And so you can create basically a function component. So a function block here, and we can rotate it. And what this is, it basically allows you to enter in an octave equation or an equation in the octave syntax that will compute an output based upon the inputs that you specify. So here we can use a multiplexer component and connect these two together. So we'll have the voltage as the first input and the current as a second input. And then we can just directly use this U1 and U2. So U1 would be the voltage, U2 would be the current, and we can just enter in this formula here. So this I naught, which is 9.8 U minus 8 times, it's an exponent of this voltage at the terminal connection plus RS, which is 0.221. And then that would be divided by this thermal voltage, 1.3867 times this alpha factor of 1.3. And then I think there's a -1. And that U2 should be multiplied by this current here. So times U2 times the resistance. And so I think that looks about right. And we can just click the checkbox so we can see it, hit apply. And then we can just start to show the results. So here we can add a scope quickly. And because we're ramping this voltage linearly from 0 to the open circuit voltage, it corresponds with time. So we can actually just generate a VI curve directly from just plotting current against time, which is effectively voltage. And then we can just add another plot. And if we want to look at the power of the panel, we can use a gain block or a product block and just take this voltage here and multiply it by the current, connect it to the scope. And then the one last aspect is just to change the runtime of the simulation, again, to say 33 seconds to run it out to the open circuit voltage, 32.9. So with that, we can just go to open up one of these scopes and make it a little bigger and go to simulation start. And we can see that I think I did my formula wrong here. because it is going the wrong way. I didn't enter in the RS and RP, so this is 415 ohms, and this RS would be 0.22. So let's rerun that. And now we can see that we have kind of the classic curves associated with the PV, right? So we have this current shown in the top plot, and we have the power shown in the bottom plot. And so you can see that the current is a nonlinear function of voltage, and you have this maximum power kind of point operating here, right? So the power will vary as a function of voltage at the terminal connection. So again, this is a really simple model built up from basic components. I guess the common question is, when Plex is an ideal circuit simulator, how do you start to model some components with nonlinearity, whether that's a diode, the diode effect associated with PV panel, whether it's the diode effect associated with something like a forward bias LED, a metal oxide brister, MOV, other protection components. So this approach of basically taking the equations that you know describe your system and implementing them just using these basic building blocks that are provided in the simulation tool is a common way to model these nonlinear effects that are relevant in PV system design and power electronic design in general. So with that kind of basic model, what we can do is I'll just save this as my desktop as a basic PV. And we can start to actually build systems that are a little bit more interesting to study. So in Plex, I opened this single phase PV panel with partial shading. And this thing has this in the background. So this here shows a more reasonable system where basically it has a 3 PV arrays connected in series. We have a DC-DC converter here. So in this case, it's just a boost, a simple boost stage. And it connects to this DC link over here. And then you have a DC to AC inverter using IGBT components. And it's just connected to an ideal voltage source through the AC grid. So the boost converter is designed to operate this PV array here near its maximum power point. And then this maximum power point tracking algorithm is implemented in the DC-DC controller to improve the performance of the PV array under partial shading condition. So these 3 PV arrays here on the left-hand side are based upon kind of fundamentally that model that we built up earlier with a few other bells and whistles, a few other additions on top of that. They also have a bypass diode connected in parallel with each one of the arrays. And that's going to be useful to discuss further during partial shading conditions. So just double clicking this, this PV array component, you can see that it's a function of the insulation, it's G input here, as well as the function of temperature, which in this simulation will just be held constant at 25 C. So if we double click this component, we can see that this model is parameterized, so you can basically punch in or enter numbers from your particular panel. So the open circuit voltage, short circuit current, equivalent series and parallel resistance, as well as the coefficients that are described in that Villalba paper that describe how the voltage is a function of the temperature, as well as the current from the PV generation is also a function of temperature as well. And so you can just do subsystem and look under mask, and you can see exactly how this is implemented. So rather than building it out of those basic equation components, just a C script is used. And it just cleans up some of the equations a little bit relative to what I showed earlier. And then it also just has a little bit of limiting and then filtering applied on top of that. So kind of underneath the hood here is that really simple component that we described earlier. So the input to these PV arrays, again, is the irradiance and temperature. And so what the simulation shows is the irradiance changing in the simulation from a uniform at the initial conditions, so at the start of the simulation, so 100% of rated insulation, And then the partial shading condition will have the lower panel irradiance decrease to 65% of rated. And so the current in the lower panel will decrease. And in the absence of this bypass diode, what would happen is there might be reverse current or power dissipated by the shaded panel. And so the difference between the generation of these upper panels and the lower one is actually shunted through this diode component. And so it avoids the problem of reverse current flow and potential hotspots and damage to the panel itself. So what happens though is that under these partial shading conditions, you end up with kind of multiple maximum power points due to the behavior of this bypass diode. So at lower generation levels, this lower panel will be bypassed effectively, and these two upper panels will be generating. And then at higher levels, you'll see that the lower panel will be generating, but at a lower level, and the response of these two upper panels will be limited by the performance of this lower panel. So actually, what we can do is go to a quick demo that pulled up earlier. And what this does is just basically copies these components from this model and does that basic sweep of the terminal voltage conditions. So we can see the power, and we'll plot the voltage against the power. And if I were just to run this simulation here, we can see that we end up with these two maximum points, right? So one of this local maxima here associated with just these two upper panels being on. And then the third point is this global maxima, which is higher. So this is maybe 1,150 watts, and this would be 1,200 watts total. So ideally, if you have something trying to track some maximum power point, the approaches here, there's different approaches to try and determine what this local maxima is. So whether it's perturb and observe or incremental conductance. But the risk is that if you don't have a control operating on top of that, you'll never know that there's a second local maxima, which is the global maximum out here at a higher operating voltage of around 80 volts. And so, and again, if you have just uniform insulation here, so we can just enter in one and rerun that, and you can see that it has a single kind of uniform global maximum at around 1,600 watts. Great, so again, this DC-DC converter here is kind of what's responsible for regulating the PV panel voltage. And so if we were to just look at how it's implemented, you can right click and open the subsystem. And you can see that it has a cascaded control approach. So in the outer loop, you have this maximum power point tracking, which looks at the voltage and current at the PV array terminal. And then it determines the voltage reference to try and regulate this DC voltage too. And then it accomplishes that regulation by actually regulating the current through the inductor or the current at this lower leg over here. So just looking at this subsystem of the mask, you can see it's using kind of digital controls from the Plecs library. So two PI regulators kind of cascaded back to back that receive the voltage reference coming from this MPP controller. And so if we were to actually run the simulation here, so just go to simulation and start, we can look at the AC side, so we can look at what's happening in the grid, and we can dive into that in a bit more detail later. But we can also look at the same curve here. So this would be the PV panel voltage, this is VPV, and you plot it against the power coming from the panel. So initially, the insulation, again, is at kind of 100% of nominal in all of the panels. And then there's a drop to this local minima or local maxima. And then after this disturbance has been detected, this MPP controller will implement kind of a search algorithm that tries to actually scan over the expected range of maximum power points and then find the global maximum as well. So you can see it might be a little small here, but there's this dot just showing that kind of what this power trajectory is over time. So here at the startup, it finds kind of this first local maxima. There's a bit of oscillations coming from the AC side, and then it operates at this maximum power point. And then again, there's this drop in insulation in the lower panel, and then the scanning algorithm finds this next global maxima as well. So underneath the what's happening actually in this algorithm is there is a C script that implements the different controls that we're trying to use for this maximum power point tracking approach. And so the benefit of the C script here is that if you were to eventually start programming a microprocessor to actually implement your maximum power point tracking algorithm, you can kind of start to prototype code here and implement the basic algorithm that you would eventually deploy to your actual microprocessor. So on the AC side is a control that again is a cascaded control approach. So we can just look at how this is implemented. And again, it's using a cascaded control approach as well as a phase lock loop, or PLL. And so the grid voltage at the point of connection is measured. A PLL, in this case, it's a second order generalized integrator, or SOGI PLL, tracks the grid voltage, determines when the PLL is synchronized to the grid, and then it has this global enable signal that closes the breaker on the AC side as well as the DC connection. And then there's a DC link controller that regulates the DC link on this side of the DC-AC converter, and that sends a current set point to this digital synchronous reference frame. And in this particular case, probably isn't worthwhile to dive too much into the algorithm, but it uses this fictive axis or fake axis emulation, where it creates an imaginary alpha beta. So the beta is imaginary, the alpha is the actual grid voltage that's measured, and then it uses just two PI controllers to regulate the flow of current based upon what it's trying to keep this DC bus voltage set to. So again, just to rerun the simulation here, on the AC side, you have this grid current start to increase during the startup. So here you have, before synchronization, there's no current, the breaker closes, and the AC current controls ramp up, and then it starts to regulate at this maximum power point. There's a little bit of oscillation again to regulating the DC link voltage on the right-hand side of the DC-DC converter. And then again, there's that change in insulation, and then the global power point is discovered again. And we can also just go back to this controller here and disable the global search. And so if we were to disable this global search, hit apply, and we can rerun the simulation and look and see where we end up in terms of grid power later, as well as look and see where our maximum power is as well. So just to show this here. So during startup, we end up at that 1600 watts, but then we end up at this lower local maximum power point as opposed to finding the actual global maximum. So again, this is a lot of controls. It's a very specific application, but it shows kind of the basics of what you can start to do in Plex and build kind of more practical systems to design algorithms, to optimize your system, to do different trade-offs of different designs. So again, this DC-DC converter here and this DC-AC are relatively simple topologies for this low power standalone inverter, but it could just as well have something more sophisticated like a dual active bridge or LLC or flyback for this DC-DC stage. There's lots of examples in Plex of that. So if you're not familiar, there is a set of library models, so demo models. So for the solar ones, they'd be in this demo models power generation, and there'd be this single phase inverter with partial shading that I described earlier, as well as say a single phase inverter. And then for power supplies, there'd be something like a dual active bridge that you can use to say start to evaluate different controls for different DC-DC converters, DC-AC, different multi-level topologies as well. So that's kind of the basics of a simple model built up from base in Plex, just showing this standalone system and designing some controls on top of that. So with that, the next kind of stage in designing a system is actually to try and prove that it works in the real world. So one kind of intermediate stage in creating products or publishing papers is to actually use hardware in the loop to validate that the control algorithm that you design will perform. So you can start to prototype code for a microprocessor, as well as evaluate it against kind of a virtual plant. So the next example is a different variation of a PD system. So this would be this neutral point clamped converter. And what we do is we take this Plex model and we're going to break it up into two components. So one component is going to be run in real time on a real-time simulator, the RT box here. And then the controller will also be generated from Plex, and we'll basically generate code for this microprocessor, interface it with this virtual plant running in real time on the RT box. And we can start to see, test different conditions, start to see how the controls actually perform running on the hardware. In reality, you can also you can perform a lot of different simulations on the RT box. So for example, different fault conditions, different kind of destructive tests that you would want to actually test in real hardware, and kind of de-risk the development process of these controls from the kind of parallel development process of real hardware from the plant. And so again, this plant is this three-phase neutral point clamp converter with a grid side filter, an LCL filter. And then the controls just is a decoupled DQ axis controls with PI controllers, both of the D and Q axis. There's also another model that we can discuss, which is a single phase inverter here. And it also has this maximum power point tracking algorithm, a voltage control algorithm for the DC link, as well as a current regulator kind of as the fast in our loop. And what's interesting about this one is that it actually has different task rates for each one of these different controls. So in order to effectively utilize the processor, it would actually run the inner loop, this fast current reference, very fast, and then it would execute this task at a slower rate for the voltage control, which provides the reference for the current. And then this maximum power point would actually be running even slower, say at 1/10 of this voltage control task rate. So, and if you aren't familiar with hardware in the loop, again, the basic concept is just to have your controller implemented on this microprocessor, kind of think that it's connected to a real plant by simulating it in real time. And so the controller will kind of sense the conditions of the plant that you're trying to control. It will perform some type of algorithm to achieve some type of output. It'll generate a PWM waveform, and the Hill platform will kind of sense all of the PWM inputs coming from the controller, as well as say other signals that you might have, other analog control signals or digital control signals, or even communications on CAN and SPI. And then it will kind of determine how the equations in the model change as a function of all of the inputs into the system. And then you'll have a set of analog and other digital signals that represent what's happening in the plant. So whether it's a grid side voltage or the current flowing through the inductor, that's all available as real measurements that you can probe, say using an oscilloscope, that are available for your controller, and then this closed loop operation happens. So with that, let me open up the model here. And so here is the model. And I also have just this little setup on my desk as well. So maybe I'll just have this camera hidden in the bottom corner that shows, again, this microprocessor connected to the RT box using this green interface board. So you have the digital outputs coming from the microcontroller going into being sensed by the RT box. It will basically compute how the currents and voltages in the system change over time, and then it'll have that available as an analog output on the RT box. So just to open this up, here we have kind of this high level overview where you have this controller and plant, and you can see that the controller actually has kind of these connections on the output of this subsystem, and these connect to the plant, which has kind of inputs as well. So just opening the plant up, you can see that you have these PWM capture components that sense the switching signals coming from the controller. And so they're assigned these variables, QU 1, 2, 3, and 4. And then these are sent to the switch controls of the NPC Plecs. These will modulate, and then you have current measurements in the filter and on the grid side component. And then these measurements are sent, so this VG and IG are the grid side current and voltage measurements, and these will be available as analog output components of the RT box. So these are our components for analog output, again, are just kind of simple Plex components that are from the library. And so in the RT box, there's a set of kind of fundamental components that you can use to program the IO of the RT box. And they're meant to be kind of pretty easy and intuitive to understand. So we just say which channel you're sensing, any scaling parameters or voltage limits that you want to have applied to that signal. So whether you're trying to, say, protect the microprocessor pins from over 3.3 volts, and then just you connect a Plex signal to that component, and it's available once you deploy it to the real-time target. So on the control side, there's this is implemented using the library components for the C2000 microprocessor. And again, it's a similar approach where you program the ADC, or the analog input equivalent of the microprocessor. And it's meant to be, again, kind of an intuitive set of parameters. So just which ADC you're going to use, scale and offset, and then any kind of synchronization that you want to have with PWM. And then all of these subsystems are basically built using standard Plex components. So whether it's C scripts or gain blocks, the DQ to alpha beta transformation, kind of all of that is built up using basic Plex components. And so this model is actually functional offline. So we can just go to simulation start. And actually, before even kind of starting to program the microprocessor or run the plant on the RT box, we can ensure that our control algorithm is running as you would expect. So in this case, it's just regulating this grid current to about 50 amps peak. And so you can see how the controls perform and evaluate them offline through simulation, and make sure that you've designed everything correctly before taking it to the real-time target. So we can just save this trace here by clicking this plot trace save button, and we can call this the offline trace. And then we can start to actually just deploy the code for the RT box plant and for the microprocessor just directly to those components from Plex. So that's done through this coder interface. And so the plant will go to the RT box that I have on my desk. And it's also set up so that there's certain parameters you can tune in real time. So in this case, we can actually change the sun intensity of this PV panel in real time once it's deployed to the target. And here I have just one RT box connected to my system. And if I click build, it will build the component, build the model, kind of generate the C code and set of equations that describe the system here, and then deploy it to the target. And then I can do the similar approach here for the microprocessor. So here it's just connected to a 28379D connected to my computer through a USB cable. And again, there's a few parameters here that are set to be tunable. So we can change the D and Q axis current references, as well as this gain of this virtual damping component. So clicking build here, it will generate code for this model. It will compile all and generate an executable, and then it will load that executable onto the target directly. So while it's building, we can just go to subsystem and look, say, at this D-axis controller, how it's implemented, and see that's using these basic Plex components, so this gain block, an integrator block, and it automatically discretizes this this PI controller from this continuous model, and then again generates C code for that, and then we'll just flash it to the target as it's happening now. So right now, this build step 3 of 3 means that it's flashing it to the target. You should see that this LEDs here have stopped blinking. So sometimes it takes a little bit while to flash to the target as well. And so one interesting thing while it's flashing is that there is a explicit kind of synchronization here between this PWM and ADC that we set up in this microprocessor kind of control loop. So we actually have kind of all of the sampling associated with ADCs aligned with the PWM generation. And then once these ADCs have the latest measurements from the real world, then it executes one step of these model controls. And so it finished flashing. And so what we can do is connect to the RT box through the external mode. And what this means is that we're just going to start streaming real-time data from this solar panel, solar system that we have modeled on the RT box. And we can also connect actually to the microprocessor and get real-time data from that as well. So if I were to activate triggering here, it just means that these waveforms are actually coming in real time from the box. So here we can see that we have this grid voltage coming in. And so this is a stiff voltage source, so it won't vary very much. And you can see that there isn't actually a very low level of output current. This is just kind of the current coming from the filter. But what I can do is I can just toggle this switch here, which enables the current regulation in the PWM output of this microprocessor. And so now we can see that this grid current actually is starting to generate. So you can see that these waveforms are updating in real time. You can start to see this DC link voltage is updating. And we can zoom in here on this grid current and have a benchmark of how our offline and real-time simulation is performed. And again, we can also look at the microprocessor here and what's happening on the controls here. And we can say start to change this grid current and change this ID rep from 0.5 to this full rated output current, and see that our controls are performing as expected. So now we're operating at 100 amps peak, or a little bit over that, as we would expect. So the ability to kind of take these basic Plex components and start getting a real controlling stuff in the real world, whether it's a virtual plant on the Hill platform or real power hardware you're connected to, is a pretty convenient way to synchronize this model that you've designed, the controls you've designed in Plex, and just kind of port it into the real world directly from the schematic. So again, that's a very quick introduction to code generation for embedded processors, for Hill simulation, focused on solar applications. And we covered a lot of ground very quickly, but I hope that you found it interesting and learned something today. So with that, I'd like to turn it over to the panel and see if there's any questions. Oh, I'm sorry, I didn't see all the questions coming in while I was talking.
Yeah, thank you very much, Brian. Before answer the questions, I would like to give the opportunity to Professor Carlos Baier to give some comments regarding your presentation, and if there are any questions, you can do that.
Thank you, Brian, for your presentation. I found it a very instructive presentation, and since last year I have used Plex from time to time. It seems to me be an excellent tool for simulating converter and power electronic systems. However, I have used Plexim before, and I think Plexim is the competence of Plex and vice versa. I don't know if you are familiar with PowerSim. Anyway, I ask you, could you tell me what advantage Plecs will have over PowerSim?
Yeah, I think one big difference between PSIM and Plecs is, they're both great softwares to use, but kind of underneath, the big differentiator with Plecs versus PSIM is that we actually have kind of a different numerical approach happening behind the scenes to perform the calculations of how things update as well. So the different numerical approach. So PSIM is based off of a nodal solver, which means that it is always using a fixed step solver or a variation thereof, whereas Plecs has a variable step solver kind of at its core. And so it may sound a bit esoteric to have describe the solvers as a difference between the two systems, but what the variable step solver allows you to do is to adapt where you will place solver instances, right? When you update the set of numerical equations as a function of accuracy, right? And so there's a lot of cases where if you have a system with one very fast dynamic, we call them stiff systems, right? So there's one very small time constant associated in your system, and you have one very large time constant. Say it's a PD system with there's the electrical time constants associated with the filtering components, but then you have a thermal model on top of that, which has a very slow dynamics, maybe on the order of seconds or something like that. And so with a fixed step solver, you're kind of always forced to have your solution times equally spaced in time, and you don't really adapt them over time. In a variable step solver, kind of once the dynamics of the very short time constant aren't particularly relevant at that kind of operating point, then you can space these solution instances farther apart. So I think that's one very different aspect, just kind of very fundamental to how we simulate power electronics is that solver. We also have a little bit different philosophies for component models, toolboxes, things like that. So it's a good product, and I think the real difference is again in the solver that allows us to simulate things based at the function of what's actually happening in a circuit as opposed to just the smallest component.
Okay. Another thing, I'm a user of a similar device to the RTBox systems. The equipment that I use is the Opal RT 4200. I can connect the Opal RT 4200 to other Opal RT systems through an optical synchronization link. And in that way, parallelize and expand a simulation. Can Plexim box to connect to other similar equipment and simulate larger systems?
Yeah, so on the rear panel of the box, there is a similar high-speed serial link. It may actually be the same connector, and so you can connect. This is the RTBox 1 I showed you. There's also RTBox 2 and 3. Basically, you can connect 4 units together on the RTBox 1. And RTBox 3, you can connect up to 8 together. And you can, again, for like solar systems where you have, say multiple converters that are interacting in a little microgrid, things like that, this parallelization aspect is critical. You can also have them synchronized. So you can have them with a common clock rate. You can have them running asynchronously. So a similar approach is definitely possible with the Plex RTBox. The only kind of item to point out is that the protocol that we use, it isn't, you'd have to basically, it can only connect to other RT boxes as it is, right? So there isn't a translator or an open protocol that we have, say, we could connect an RT box to your Opal RT system. Although some folks have expressed interest in that. Okay,
thank you very much for your presentation. Marcus, I don't know if Félix have some questions.
Thank you. Thank you very much, Carlos. Félix?
Yeah, I'm here. Thanks, Marco. Brian, very nice presentation, very brief. I think you actually talk about a very wide topic and the use of the RTBox and all its features in a very short time. So thank you very much for being that precise and comprehensive with the tool. So my question is regarding the, can you hear me, Brian?
Yes, I can.
Yeah. So my question is regarding the simulation speed, because when you have like a small system like the one you showed, like everything runs fast and everything like kind of goes smooth. But whenever you have to implement large systems and you have like maybe hundreds of switches in a simulation, and then the things start to go a little bit slower and it's more complicated, and there are some tricks to make the simulation run faster. So I would like to ask you whether you can give us some of those tricks, like for example, you have some H bridges that you can put it like in a matrix form, right? Like in a state model, so to make the simulation run faster, or also how to configure the solver. So which are those aspects that we also have to keep in mind when we have to simulate a larger system? This is one thing. And the second is, when you use the RTBox, it is possible to make real-time simulation without using the external microcontroller card?
Yeah. So for your first question, just so I understand, is it about the Plex kind of offline simulation, or is it specific to? Okay. Okay. Yeah. So I think for larger systems, obviously, as your system increases in complexity, right, it takes more time to compute, right? Just with more complexity, there is more computation. So I think for one of the little tricks, we actually apply this in offline simulation as well, is to try and find ways to decouple the set of equations behind your system, right? So for like a PV system, you would have, say, or for a microgrid, you have several DC-AC converters connected to say a DC bus or AC node, and then you'd have all of your DC-DC converters. And there's certain ways to structure your model where you can actually separate numerically kind of the DC-DC side from the DC-AC side. And so what that does is basically Plex has a set of state space matrices that describe the system. So the say capacitors and inductances, or each one of those has a state associated with it. And you can, when all these systems are coupled, you end up with these rather large sets of matrices, right? Mm-hmm. But what you can do is at kind of relatively stiff states. So if you have, say, this DC link capacitor, you know that capacitance isn't changing drastically from time step to time step. And so what you can use is actually use a controlled voltage and controlled current sources. And maybe if I can actually just share my screen quickly, I can pull up an example. I can send it to you later, but yeah, basically it's the idea that you would use, say, a voltage measurement on one side and a controlled current on the other side, and you can decouple these systems, and that actually goes a long way, especially when you have lots of systems with multiple switches as well. The other thing is once you start to have hundreds of switches, sometimes that trade-off between the variable time step solver and the fixed time step is something to consider. So there may be some advantages to evaluating, benchmarking those two against each other, seeing how they perform as well. Again, it's always kind of a model by model question, whether you have some very short time constant, whether there's something that can be implemented better, say using a C script as opposed to.
Right, but I mean, I think that the bottom line of this conversation is for the audience to let them know that whenever they approach to a large system, they have to take into consideration some design rules to make the simulation run faster, right?
Yeah, yeah, yeah. So with that, maybe I can share. Let's see if I can pull the demo model. Let's see if I can I don't have it readily available. But yeah, I think that design rule of splitting the system. Actually, let me share my screen quickly. Share screen. And So one trick is that in this solver setting, so the simulation parameters here, you can actually see that state space splitting that I mentioned earlier. You can actually disconnect. And there's a tutorial on the website that I can point you to actually that describe this in the context of real time, but again, it's equally applicable to offline simulation. And so it uses this display state space splitting. And so what this does is it basically actually lets you know in your circuit what the sets of equations are. So if I were to run this model and check this box and hit apply and rerun this here, there actually is going to be this little icon in the bottom right-hand corner, and it'll actually show you what the electrical systems are. So I can click this and see here, we can see that the way that this model is constructed is that the converter, the grid side here is one component, and on the left-hand side, if we click this one, actually the DC side and PV array is actually decoupled numerically from the AC side. And this is kind of one critical approach to speed of the simulation here. So if we were to actually look underneath the mask here, subsystem look under mask, kind of the way that this happens offline is because we have this this gyrator component here, which basically uses this voltage source to emulate what the switching behavior is on the grid side. And then you measure the current flowing through that voltage source and apply that to this DC length. So in here, it's in the switch, but it could just as well be across this voltage, the voltage across this capacitor here as well. So that's one trick. Yeah, the other aspect is picking the right solver. So whether it's the stiff or non-stiff system, newer versions of Plex have this auto feature, which allows actually will switch the solver during the simulation. So if the system goes from stiff to non-stiff over time, that's one advantage. And again, the solver has this fixed step option where here you could, again, these larger systems with 100 switches, this fixed step might be a nice tool to evaluate. The other thing that'll slow the simulation down is the presence of algebraic loops, where you basically have some type of control that depends on the output, depends on the input. And so you kind of run into this circular set of conditions. So eliminating algebraic loops from your model, especially if you have something copy and pasted a ton of times, these algebraic loops can really slow things down quite a bit. So you can break those either by reformulating your equations, or you could say add a delay or filtering component in series with those set of calculations as well. So that's another thing to be on the lookout for.
Thank you. Thank you very much. And yeah, the last question regarding that issue was when we don't have the RT box, right? So it's an offline simulation. Mm-hmm. So when you have the RT box, but you don't have this output controller board, is it possible still to run the simulation faster on the ActiveVox itself, like kind of a real-time simulation?
So you can, but one challenge with that is the modeling of the switching devices, right? So getting into kind of the internals of the RT box is that it operates on a system on chip. So there's an FPGA fabric, and then there's the CPU. And so the CPU runs C code that's generated from the model, and we use the FPGA fabric to perform kind of an oversampling of the digital inputs, and those give you enhanced fidelity when you're measuring PWM signals, right? So you can actually know where within kind of these regular interrupt-driven executions of that C code that describe your model, you can time average the PWM input so you maintain the volt-second balance of that particular switch. And when you just run things without having that PWM input sensed, the PWM fidelity, or kind of the fidelity of your switches, is really directly coupled with your time step that you choose, your discretization time step, that interrupt that describes how often you run that C code. So the answer is yes, you can run something like that, but it won't generally have as good a performance as it would if you had the benefit of that oversampling algorithm that we run on the digital inputs. So generally the performance won't be as good as if you were to connect it to cluster. That being said, a lot of times what we do in some of these demo models here is we just use a loopback cable. So the cable, the connections on the front panel of the box are just these standard connections, and you can just directly wire the digital outputs from the RT box back into the inputs. And so there you can actually have this mixed mode where you take advantage of the FPGA fabric in generating and sensing the PWM signals, but you still run your C code. You still run your model again as you would normally. Okay.
Is it allowed? It's allowed to feed back the cables just directly, just loop them.
Yeah.
Okay.
And several of the models that come with it use that approach.
That's a super great feature, because then you really speed up your simulation time when you have some large system. Thank you very much, Brian. So that's from my side, Mark.
Thank you very much to Carlos and Félix for their comments and questions. There are few questions from the audience, especially for Brian, but also Carlos and Félix can help to reply them. And one question from Pedro Galdames is if there are some special libraries to use C with Plex.
Yeah, so Plex actually comes with its own kind of internal C compiler. It has access to standard C libraries, math.h and so on. You also have the ability to include external libraries that you might have, again, using just pound include. And then the other option is that you can write C code externally, and you can compile it into a DLL. And rather than having the C code in kind of that C script interface that I showed earlier, you can have a DLL import that basically calls a compiled executable or compiled DLL that you built using whatever libraries that are available to you.
Super. Thank you. There are also one question from Angelo Canales and Christopher Ruiz. They ask if you can explain how to add the PV strings to the libraries, because it is not included by default. So they have these issues. So can you comment about that?
Yeah. That's a good question. So, one of the things I kind of pointed out earlier is a difference in philosophy in Plex to some degree versus other simulation tools, where for including things in the standard library, you guys are researchers and engineers, and you need to study certain cases and derive your own models that are really specific and tailored to what you're studying. And so for modeling the PV panel, there isn't, there's one model that's kind of very often used, but it may not cover all the use cases that you need. And so for us, for these components where there's so many variations and different modeling approaches, PV panels, batteries, like lithium-ion battery models and so on, we generally don't include them as standard library components. But what we do is we build up demo models that, implement these subcomponents and that are based on common approaches in the literature. So actually for that specific model, again, I can share my screen quickly. So it would be in the demo model library. So this help Plex documentation, and it'll pull up the screen here. And then you can look in Plex demo models, power generation. And so there's a few different PV models here. One of them actually based off of the lookup table based approach. One of them is based off of that equation based approach. This is the one I showed earlier. If you click this link in the upper right-hand corner, this Plex model, then you have access to this component, which is kind of what I showed earlier. And again, it says that's based off of that Fialba paper mentioned earlier. So again, there isn't a library component as well, but you can also build up your own custom library. So in my case here, I have my own little library component of different controllers and microgrid components that I find useful. So you could just as well take this and create a custom library that's your own, set of PV panels or converters or controllers, whatever it might be, and reference it in your own one.
Super. Finally, can you share the website of Plexim? Because I have visited this, and it's very friendly, and there is a lot of information. So for the audience that are starting to use Plex, or that have the intention to use Plex, can you show what they have in the website, especially all the tutorials and the information they can have access?
Yeah, let me pull up Plexim website. And go back to screen share. So for learning about, I guess the documentation we have available is when I'm starting to do a new application. Oftentimes, again, having used Plex quite a bit, I just go into the demo model library and search for the keywords that I'm looking for, right? So if it's a lithium ion model or a dual active bridge converter, I would just often just pull up the help, and search and go from there as well, right? And so for even things like scripting and so on, a lot of times I normally start, not on the website, but rather on the help that we have. But sometimes it isn't so easy, or you want a little bit more structure to actually understand Plex. And so what we have here in the support is for new users, I think the tutorials are helpful. So here there's a set of tutorials based on, they're broken up by category. So there's several ones for Plex. So for example, if you want to learn how to use the C script block for controls or for generating PWM signals, as well as DLL block or using mechanical domain. So there's a set of kind of basic tutorials here. So they have a PDF that will, walk you through step by step what to do. So as a little bit of background, then it says, open Plex and add a heatsink and do A, B, C, and D to gain some type of understanding for how Plex works. Some of them are accompanied by a brief video, and so the video may not correspond one-to-one and show you step by step, but it corresponds to the general ideas of what this model does. So, and here you can have an associated video for this thermal import wizard that's related to thermal simulation, this thermal simulation model. So there's multiple pages in the event you're looking for something and it's hidden. And there's also a set of tutorials you can sort by the, say, RT box, by Plex. If you want to look at, say, embedded code generation as well, you're getting started with that. There's a tutorial there. And then the last little thing, and you can download the documentation, but it's a replica of what's there in the help. And then the other thing is just, if we have a ton of YouTube videos, we've done a lot of webinars over time. If you're trying to understand something specific, you can just reach out to support, and we'd be happy to point you in the direction of some type of reference to help you understand something specific on Plex. So don't be shy, and please do reach out if there's something that you're looking for and you just can't seem to find it.
Super, thank you very much.
Yeah.
Okay.
There's also is a forum as well. So you can also post questions there, and folks have a lot of other questions that they may come up over time, or your question may have been asked already as well. So I've answered a few of these questions myself, so I'll definitely see that and be able to help you out if you have a question there.
Great.
Sorry to interrupt.
Great, thank you. It has been a very interesting presentation. Thank you very much, Brian. And now, in order to finish our meeting, I would like to ask to the panelists, and finally to Brian, to provide their final reflections and comments and conclusions. Carlos?
No, so to say a very good presentation, very instructive, and I congratulate to Brian and the software and system that he showed us. That's all.
Thank you very much, Félix.
Yeah, well, first of all, thank you very much, Brian. I have also been in touch with Plex for several years already. We implemented this software for our power electronics lectures here at the university, and it has been really, really helpful. Students really enjoy to learn in an easy and simple way power electronics, which is usually not like that friendly subject at the university, you know, a lot of equations and math. So I think for me, has been a really, really interesting tool. The software itself and also the RT box at the laboratory speed up the process for jumping from simulation to real world implementation, especially for students who are not really doing PhD, but they are 1 year, for example, at the lab or 1 semester, and they want to run something. This is a very, very intuitive tool. So I encourage all professors and university who has not been using this tool that make a try. It really speed up the process and it's really simple. And best of all, the students feels like they are learning something and they are interested in on the software. So at least for me, it has been a really, really nice experience. So thank you very much, Brian, for your presentation.
Thank you very much, Felix. Finally, Brian.
Yeah, I just want to thank everybody for your interest and for the questions you asked, especially Carlos and Felix. Hope that they help provide some type of insight for Plex and help you guys use the tool more effectively and give you some ideas for other avenues that you can use to provide the software. So thank you, Felix and Carlos, and thank you, Marco, for organizing this event as well.
Super. Thank you very much to everyone for participating in this cycle of seminars. And we invite you for the next 2 weeks. We will have another session of this webinar. The presentation will be in Spanish, so you will receive in the next few days an invitation. Thank you again, and I hope see you soon next time.
All right. Thank you, Marky. Bye-bye.